Now, visually, holding costs look like this. The cost is the vertical axis, and the order quantity is the horizontal axis. Holding cost is Q over 2 times H. H is the holding cost per unit. It does not change. Q over 2 is the average inventory level during the year. So holding cost is Q over 2 times H. As quantity increase this way, okay, so as the quantity increase this way, the Q increases, the holding cost actually increases. Now the ordering cost is different curve. This ordering cost, again, now the vertical axis is the annual cost and the horizontal axis is quantity, just as before. And now our ordering cost going to be a curve. It's not a straight line. It is D over Q times S. So D over Q here is the frequency of ordering. So this how many times we order. And S is the ordering cost each time. Right? So D again is the demand, and as the Q increase, okay, the ordering cost line actually decreases because Q is divided by D. So as Q increases, D divided by Q times S decreases. Now, putting together, we have holding cost and ordering cost. They look graphically like this. And we can see that as the Q increase, one line goes up, the other curve goes down. So intuitively, now we probably can think of some sort of achieve a balance. And at this balance point, somehow, we have some optimal result. The total cost is holding cost plus ordering cost. Okay, so it's a summation of these two. So mathematically, it's TC equals to Q divided by 2 times H plus D divided by Q times S. All right. So one thing though I have to mention is that our goal here is try to find the optimal ordering quantity that gives us the minimal total cost. Minimal total cost. All right. So again, our intuition is we are trying to find some balance point. Visually, that balance point actually is right here. It's a Q star point. At this point, holding cost on the holding cost line and the ordering cost line cross right here, which means at this point, the holding cost equals to ordering cost. This is the point. Okay. So, and these two lines cross each other. Now, when the holding cost and the ordering cost are equal, we know that the holding cost equals to Q times H over 2, and ordering cost equals to D times S divided by Q, so these two equal to each other, which is the same thing as holding cost equals to ordering cost. Now, to solve this for Q, we can easily find that Q star equals to 2 times ds divided by h take a square root, which is 2 times annual demand times ordering cost divided by annual holding cost per unit. What we can do is we can also use calculus. We take the derivative of the total cost function and set the derivative equals to 0. And we solve for Q. So the first derivative of total cost, if we write it down, it is h divided by 2 minus d times s divided by q squared. We set it equals to 0. Then we solve for Q, we get same answer, Q star equals to 2ds divided by h. Remember when we learn the calculus, we know that we also need the second derivative to be positive in order to find the minimal. If the second derivative is negative and the first derivative is 0, then what do we find is the maximum. So now we have to verify that the second derivative is positive. Here it's very easy. We're not going to go through the details, but if you take the second derivative of this, of the TC, sorry, this is the first derivative. So if we take the second derivative of TC, then what we get is actually positive. So for Q, we do have the same answer as before. It's Q star equals to 2 times ds divided by h. So this is how much we're going to touch the calculus. If you're you have some questions, just let me know and we can talk about that after the class. And we usually are not required you to be familiar with calculus in exams, so don't worry too much about it. Now anyway, we find that EOQ, the economic ordering quantity, equals to 2ds divided by h take a square root, and that is the quantity that gives us the minimal total cost. So now let's look at an example. So in this example, we have this a small store selling 2 little boxes of soft drink. The demand rate is 10 units per day, and the annual demand is 3,650 units per year. The purchase cost is $1 per unit, and the ordering cost is sorry, let me go back. The ordering cost is $20 per order. Holding cost is, in this case, we're gonna if we take the rate as 15% per year, the annual cost per unit per year, which is the capital H we use here in our formula, is 15 cents per unit per year. That's the one we're going to use. So we plug in the numbers to this equation here, to square root of 2ds divided by h. So demand is 3,650 units per year. The S is the ordering cost is $20 per order, and holding cost, which is capital H, is 15 cents per unit per year. We get $986.58, which we cannot order a fraction of the unit, so we run it up to 987 units. Okay, now since we also can since we know the optimal ordering quantity, we can also calculate the total cost. Total cost is the annual holding cost plus annual ordering cost. So we basically plug in the numbers to this equation, and we know H is 987, H is 15 cents. So annual holding cost equals to $73.99. And annual ordering cost is demand 3,650 divided by Q, which is 987 times S, which is ordering cost of $20 per order, is exactly $73.99. So annual total cost is the annual holding cost plus annual ordering cost. It's right here. It's $147.98. And by the way, we can see that the annual holding cost and annual ordering cost, they are actually same at 73.99. So if we go back, we can see that in our graph here, there is a balance point, right? The balance point is exactly same as this one. Okay, so that is our economic ordering quantity. Economic ordering quantity.